Tertiary everybody. So just now we have done with law of induction, that is induced EMF is equal to minus and d phi d. This is the rate of change of magnetic flux. And just now we explained the significance of minus, that is explained by our lenses, and the minus indicates the opposites. That means, again I am repeating, minus indicates that the direction of induced currents, the direction of magnetic field due to an induced current opposes the rate of change of magnetic flux. Rate of change of magnetic flux. If I say the flux is increasing, this magnetic field produced by a induced current decreases. All right. If coil experience decreasing magnetic flux, then the direction of magnetic field due to induced currents increase the decreasing magnetic flux. So this is the point. All right. So now what I'm going to do is I'm going to do what we call as motional EMFs, right? Motional EMF, right? Motional electromotive force. So I have a uniform magnetic field. This is a uniform magnetic field, and the magnetic field is into the plane. Direction of magnetic field is into the planes. I have a rectangular coils. That is rectangular coil. That is rectangular coil. Rectangular coil. That is N R S N, and this is a metallic rectangular coils put in a uniform magnetic fields, and I have a rod, metal rod. I have a metal rod, PQ of length L. All right. So what we are going to do is I allow a metal rod to roll on this rectangular coil, right? So if I say if it is moving in these directions, all right, and the magnetic flux across this closed loop, magnetic flux across this closed loop is going to change. Why? So I just say magnetic flux. What is magnetic flux? Magnetic flux is equal to EA. And what is the area, right? Area is going to be XL. Alright, area is going to be XL. So if a rod moves, X is going to decrease. If rod moves, X is decreasing. That means flux is changing. That means flux is changing. Alright. So therefore, what is the rate of change of magnetic flux? So I just say the rate of change of magnetic flux. Rate of change of magnetic flux is equal to BXL. Okay, so this is equal to B, and then L is constants and dx by dt. Dx by dt, right? So X is decreasing. This has to be a minus V, right? Why? V is equal to minus dx by dt. Now I am going to apply Friday law of inductions, right? So we have a Friday law of induction says that Friday law of inductions, law of inductions says that this is equal to minus d phi b by dt, and which is equal to minus into minus is plus, minus VLV. Okay, so induced EMF is equal to VLV. This is V, this is V. I'm sorry, this is V, this is V. Alright, this is motional EMF. So motional EMF BVL. This is motional EMF. So that means if you move faster, then EMF induced is going to be greater. If you move little slow, EMF is going to become less. If V is 0, if V is equal to 0, then EMF is going to become 0. Alright. Now let me show you a direction of a current. Let me show you a direction of current, right? So it is decreasing magnetic flux. And this coil experience a decreasing magnetic flux. If this coil experiences a decreasing magnetic flux, then current due to this directional current in this coil has to be is such that magnetic field due to induced current opposes the change. That means decreasing means it has to increase the decreasing magnetic flux. Alright, again I am repeating, right? Repeating that is the direction of induced current is such that magnetic field due to induced current increase the decreasing magnetic flux. How to increase the decreasing magnetic flux? I just put this. These are the magnetic field due to, these are the magnetic field due to induced currents, right? So therefore, what about the direction of current? Like this is the into the plane. So I'm showing you the directions, right? So therefore, the direction of current is going to be this. Direction of current is going to be this. This is the direction of current. This is the direction of current. This is the direction of current, right? And what about this, right? So look at here. V moves in these directions. V is the velocity, and the positive charges are moving in these directions. And the loading force is down, so the positive charges are moving down. So so you find here a positive charge. You find here positive charge. You find here negative charge. You find here negative charge. So this is the point. This is going to be our this is the polarity. The EMF is induced across this rod, such that Q is going to become a positive charge and P is going to become a negative charge. So this is what we have, right? And I will give you this. Okay. I can prove you in another form, right? What is the walk, right? All right. We say that work done. All right. This work done is going to be force into I say potentials multiplied by charge, right? Potential multiplied by charge, right? And how much is work? All right. How much is work? All right. So let me do like this, right? And then work is equal to this. Work is equal to VBL, right? That is, I will give you this. This is something like this, right? How much work, right? So when you talk about Lorentz force, work is equal to force into distance. Work is equal to force into distance. And what is the distance? Here, this is another proof, right? What is the distance? Distance is going to become L. This is the length of flow, right? Why? Because there will be a transfer of a charge across this. Why? Because if you move in this, and if you move this rod, there will be so many free charge carriers. So therefore, there will be movement of free charge carriers, and movement is going to do along this length. So this is L. And what is the force? Force is equal to QVBL, right? This is all right. This is one case, and then this is normally done in this is a potential V. I'm talking about this is capital V. This is potential V. This is a velocity V, right? So now, what is the potential which is equal to nothing but EMF? So potential or V EMF is equal to work done divided by Q. Alright, simple. And what is the work done? Work done is equal to QVBL divided by Q. Q cancel out. EMF is equal to VVL. So this is the other way of deriving this formula. Same. This is the more mechanical part. Why? Because I allow a charge to move, and I see that charge are moving. That is why charge experience Lorentz force. All right. And in this case, we straight use law of induction, right? So this is the point. Now, what I would like to do is, there will be a current in this coil, there will be a current in this rod, and we would like to see what about the direction of current, what about the direction of force, right? So look at here, this, and you are pushing in this direction so that it is moving like this. However, the rod experience, this is direction of current, right? So this is direction of current, and I'm going to use here Lorentz force. So Lorentz force is equal to QV cross B. All right. So what about Lorentz force here? All right. What about Lorentz force here? Right. Lorentz force here. All right. So this is the point, right? So this is the Lorentz force. This is the force, and this is going to be external force. This is going to be external force, and this is the force due to magnetic field, right? I call as Lorentz force. Lorentz force. And now again, this is very much consistent with law of conservation of energy, right? So these two forces are equal and opposite, right? These two forces are equal and opposite, so therefore this could move along. This could move with the constant velocity. This could move with constant velocity, right? So again, this is very much consistent with law of conservation energy. I will explain you later, right? This is how we have done it, right? So this is another diagram. So I will explain you again this. In these diagrams, what we are trying to show you is velocity is in these directions. So the area is increasing area directions. If area is increasing, look at here. If area is increasing, then magnetic field due to induced current has to decrease. So therefore, direction of magnetic field would be like this. Right? It decreases the increasing magnetic flux. So therefore direction has to be like this. Direction has to be like this. And then this is going to be a positive terminal. This is going to be a negative. This is how EMF is done. Right? This is how EMF is done. Alright? So this is one point. This is what we call as motional EMF. This is what we call as motional EMF. Alright, now next is energy considerations. Alright, so talking about energy considerations, just now I talked about this, alright? When you talk about energy considerations, right, what the rate of energy produced? The rate of energy produced in case of motional EMF, right? So rate of energy produced in case of, let's say I have a rod like this. This is say I'm going to take say, right? So these are the magnetic field. This is P, this is Q, M, N, R, S. This is rod, and rod, that means you are pushing, right? V tells you directions and tells you direction of external force. Alright. Now there will be energy, there will be a current. This is the direction of current. Alright. And let's say that the resistance of this coil is R. So R is a resistance of this coil. Let's say resistance of rod PQ. R is a resistance of rod PQ, right? Then what about the current, right? So current is going to be EMF induced divided by resistance. This is the current, alright? This is going to be a current, right? So if this is a current, now what about the force? What about the force acting on this, right? That Lorentz force, alright? That force, just now I told you that force has to be in this direction, right? Force has to be in this direction. And the force is equal to ILB, right? Force is going to be equal to ILB. This is the force. And now look at here, this is the force. And how much is I now, right? And look at here, and then what about EMF? EMF is equal to BVL, right? This is motional EMF. This is the motional EMF. All right. So this is equal to BVL. All right. Having this, now I just say that I is going to be BVL divided by R, and then force is going to be that force, that Lorentz force. I'm going to talk about Lorentz force. This is a Lorentz force. This is Lorentz force. Lorentz force means magnetic force. Yeah. Force is equal to, I substitute the value of I. V square, V and L square divided by R. BVL. This is the force. This is the force. And then mechanically, what is power? Power is equal to FB. I will derive this. This is done in class 11, right? What is power? What is power? Power is rate of doing work, right? Rate of doing work, right? So what is force? Force is equal to what is force? Work is equal to rate of doing work, right? Power is rate of doing work, right? So therefore, what is work? Force into distance, right? Let's say distance and t, and x by t is going to be a velocity. So therefore, power is equal to VV. This is just the recapitulation of class 11. This is a recapitulation of class 11. So that this tells you how P is equal to FV, right? Having P is equal to FV, now I just say our power is equal to FV, which is equal to V square L square equal to R. So this is the power, and this is the rate of doing work, right? So this is the rate of doing work, and this is the rate of producing electrical energy. This rate of producing electrical energy, right? So this is the force has to be in these directions. Force has to be in this. So this is the mechanical. This is the external force. So we are applying external force in these directions, and there will be force in opposite. That is the Lorentz force, and these two forces are equal and opposites. External force. I just say Lorentz force, and these two forces are equal opposite. That is why this is moving with velocity. I'll give you an example of springs, right? We talk about spring, right? Class 11, right? So if I push, there will be a restoring force, and then the restoring force and external force are equal. Therefore, springs move with some constant velocity, right? So this is the same here. So this is the power. This is the power, right? And then another way of proving is electrically, right? I can prove this. What is power? Power is equal to I square R. Power is equal to I square R, right? So what is I? I is equal to BVL R whole square R, and this is equal to B square, V square, L square, R square, R cancel out. This is power. So we can do it in both the way, right? Mechanically this, and electrically I can prove this, right? And then one more I would like to do is, where to do? One more I would like to do is I would like to give you a relation between rate of the change of magnetic flux and the change of the rate of flow of the amount of charge flow, right? So what is that? EMF is equal to, let's say this EMF is equal to d phi by dt. This is magnetic flux. This is magnetic flux, and then we say that this EMF is equal to IR. EMF is equal to IR, and then what is I? I is equal to delta Q by delta T. All right, having I here and delta QB. This is the change of magnetic flux. And then this is equal to delta Q by delta T R, delta cancel out, then this is equal to this is how I establish a relation. This is the amount of charge transfer is equal to rate of change of magnetic flux divided by resistance. Rate of change of magnetic flux divided by resistance, right? So this is all about. Again, if I would like to explain you the conservation of energy here, again I would like to do it. Not that very important for examination point of view, that conservation part, but however it is very essential if you could able to understand, right? So I will tell you this, right, just for your understanding only. Conservation of energy. Let's say I write again here rod PQ, and again I will prove you in a converse way, right? Proving in a converse way, right? So let's say that I just take the converse of Lenses law. So Lenses law says that current has to be in these directions, but I take that current is in the opposite directions. But I take the current is in opposite directions, and this has to be like this. If this is so, this is the external force you are pushing, right? External force and the velocity, right? And now we would like to see what about the Lorentz force, right? So where would be a Lorentz force? Look at here. This is the charge moving up from Q to P. Right? I'm not taking here electron. Why? Because electron is just the reverse of positive charge, right? So instead of taking electron, I'm taking a positive charge. Look at here. And what about direction of external force? What about the direction of Lorentz force? This is the Lorentz force. So now look at it. Here the Lorentz force direction and external force directions are along the same directions. That means I push for a short period of time, and then it starts moving on and on. It starts moving on and on. That is what means the perpetual motions. It starts moving on and generating a power, right? And generating a power. How much power? B square, V square, L square by R. This much power is generated, right? This much power is generated out of nowhere, right? Out of doing no work. And this is inconsistent with law of conservation of energy. So therefore, this sign is wrong. So if this is so, if I take these directions, then this force has to be in these directions. Therefore, unless I push this, alright, there won't be any current produced, there won't be any electrical energy produced, right? So this force is equal to that force, alright. With this, alright, this one more, right? Now last part of this is eddy current, right? So alright, so far we have been dealing with a wire, alright, current induced in a wire. So far we have been dealing with current induced in a wire, alright. So now what happened is, what about if the rate of change of magnetic flux is subjected to a bulk metal piece? If a bulk metal piece is undergo a rate of change of magnetic flux, what is going to happen? Answer is simple. There will be a current. If there is a current, if there will be a induced current, what about the direction of the current? If it is a wire, the current goes along a wire. So this is the point, right? So this was first discovered by Nigel Foucault, right? So he found that when a bulk piece of conductors are subjected to a changing magnetic flux, then there will be a current, right? And the direction of currents, is not like the direction of current in a wires. So the direction of currents resembles, the pattern of direction of current resembles the swirling eddy in a wire. That means that it is a swirling, or it is a winding motion, right? That means it goes like this. This goes like this. This motion. This is what we call as a swirling eddy in a water, right? Or whirlpool. You might have heard of a whirlpool, right? If you see a whirlpool's direction is this. If you see either direction is this or direction is this. So entire water goes into some point, right? So water goes like this is what we call as a whirlpool, right? And likewise, so the direction of current, the direction of currents or the pattern of a flow of current resembles what we call as a swirling eddy. So therefore this current is what we term as eddy current. So whenever we talk about eddy currents, the current is induced in a bulk metal piece. Right? So I read it, when bulk piece of conductors are subjected to changing magnetic flux, induced currents are produced in them. However, their flow pattern resembles a swirling eddy in water, and these currents are called eddy currents. So eddy is the type of motions. All right. So the direction of current is like eddy. Therefore, it is what we call as eddy current. Now, so this was found, right? And I have a magnet. This is the metal piece. I allow a metal piece to swing between a magnetic field. Alright, this is north pole, this is south pole. So the direction of magnetic field is like this. Direction of magnetic field is like this. I'll use that pen, right? This is direction of magnetic field. Now, the direction of induced current is given by that Lenses law only, right? So when this metal piece enter through this increasing magnetic flux, if it is increasing flux, magnetic field produced by eddy current has to decrease, right? How to decrease? Right, this is magnetic field due to. This is not bind, right? Sometimes you've confused. This is bind, right? This is induced, right? So how to get this is, look at here. Look at here. Direction of this magnetic field opposes this. Why? Increasing magnetic flux. Alright, when these metals enter through this, when these metal piece enter through this magnetic fields, it experiences an increasing magnetic flux. If experiences an increasing magnetic flux, then magnetic field due to current opposes the change, so therefore this is magnetic field, right? Now when this metal leaves this surface, it experiences a decreasing magnetic flux. So decreasing magnetic flux, so therefore it has to increase the decreasing magnetic flux. So this is the direction of magnetic field. Alright, this is direction of magnetic field. And that is why direction of this. Alright. So therefore this experience repulsions. This experience repulsion and this experience attractions. Why attractions? Fields are along the same directions. This field is along the direction of this magnetic fields. Why repulsion? This field is opposite to the direction of magnetic field. So therefore it induces damping, right? You say damping is done, right? Damping is done, right? So if you let this pendulum to oscillate in a free air, the time to stop is going to be very long. Why? Because the damping is only going to be due to air damping. But when you allow this to, how he came to know is when he allowed this to oscillate in a magnetic field, the damping there is extra damping, so this come to rest very fast. And what is the reason? There is another. This is due to magnetic effects. This is due to magnetic effects. This is what we call as Eddy. Now what happened is that now how to reduce it, right? Now he performed this experiment, right? He cut this, all right? He cut this, and what about this? I'll just say, right? What about magnetic moment? This magnetic moment is going to be IA. This A is the area of this coil or area of this metal piece, right? IA. This is the magnetic moment. Now, when I cut this and allow to swings, and the time to stop this is much longer than this. Much longer. Time to stop this is much longer. Why? Because it has less damping. Why? Because you cut these pieces, so area is going to become less. If area become less, magnetic moment will become less, magnetic field become less. So therefore repulsion is less and attraction is less. So therefore it takes more time to stop. So this is how you reduce, right? So look at here, areas are blessed, and the curve should be such that the pieces, the curve should be along a direction of magnetic field, right? Curve should be along. That's I'll explain you, right? And so this is what we call as Eddy current, right? So the limitation, right? These Eddy currents, because of these currents, this harmful, right? That means this, because of these Eddy currents, the metal coil gets heats up. Because of current, it gets heats up, right? So therefore, the disadvantage of Eddy current is that it heats up the coil, right? It heats up the coil. Normally, when you have iron core, right? You put iron core and then transformers. Maybe you will study that later, right? Transformer, you use the iron core. So if you put an iron core, if you wind wire over it, then there will be an Eddy current, and then the iron core get heats up. Then there is energy waste, right? There is loss of energy by virtue of converting energy into heat, right? Now the point is how to minimize Eddy current. How to minimize Eddy current? The simple concept is you have to reduce the current. You have to reduce the area, right? So magnetic moment is going to be IA. What you are going to do? You are going to reduce area. How to reduce area? We shall cut metal piece into a laminated, right? So I just laminate iron core, right? This is how we laminate iron core, right? And I just laminate iron core. If I laminate iron core, what happens is And then I put between every laminated coil, I put insulating medium so that there won't be any short circuit, right? So this is what we call a lamination, so laminated coil, right? So this is the effect. This is the right. If I don't laminate, this is going to be a magnetic field, and area is going to be so big. Then damping is going to be more, heating is going to be more, current is more. So instead what I did is I laminate this. When I laminate it, then the area is going to become less, and then eddy current is going to be less, alright, and then area is going to be less, then magnetic field is going to be less. So this is the very, very important application, right? And how to arrange, right? How to put this in the magnetic fields, right? So the laminated iron coil should arrange along magnetic fields. Laminated iron core should arrange along magnetic fields so that induced magnetic field would be least, and eddy current would minimize. All right. So this is one very important, right? This is the transformer. Later you will study, right? Next chapter. And then again, eddy current has advantages and application of eddy current is magnetic brake in a trains. I'm not going to go detail, right? So electromagnets are used for braking, right? Electric train brake. Why? Because because of electromagnets are generated during the time of brake. So therefore there is eddy current is produced. All right, because of which it opposes the motion. So therefore this is what we call as magnetic braking in a trains. Another one is electromagnetic damping, right? Electromagnetic damping means this. You might have come across the galvanometer and all. When you switch off, galvanometer come to rest immediately. Right? Otherwise, it has to swing. Why it doesn't swing means because of magnetic damping. Right? When it try to swing, this will try to oppose the swing. So this is what we call as electromagnetic dampings. And induction furnace means we use electrical heating, right? That means we have induction cooker, right? And then this is also used in a big factory, right? For melting iron ore and all, right? So this is used, right? And electric power meters, right? So you see, maybe these days you don't see it because we have only digital electric power. Otherwise, when we have analog electric powers, what you see is that because of eddy current, you see the silver-like wires start rotating, right? So this is all because of eddy current, right? So with this, I'll stop. All right. So next class, I'm going to finish this chapter. Thank you.